I'd like to now talk about the Dieckmann condensation. The Dieckmann condensation is related to Vergleisen except that it involves a diester, which means we end up with a cyclic ketoester as a product. Alright, let's take a look at the mechanism for this and you'll see what I mean. So here we've got a diester. Again, note that the ester groups match the base as well, so we've got OMEs everywhere, including in the base and the solvent. And what's going to happen here is pretty similar to what we observed in the Gleisen reaction. So what can happen is that one of the alpha hydrogens can be removed. In this instance, we've got a symmetric diester, so there's no problem with choosing either one of these alpha hydrogens. If it's asymmetric, it does matter, and we'll be seeing that a little bit later on. Alright, so that's the first step, is the removal of the alpha hydrogen. Which leaves a negative charge. Leaves a negative charge on this C, and what's going to happen is that the negative charge will come in and attack the C double bond O on the other side. And that leads to a cyclization. Now we can count this, and what I can do is I can count from this end. 1, 2, 3, 4, 5. And you see what we end up with will be a 5-membered ring. And on the 1 position I'll have an O negative and an OME. And on the 5 position, let's count this around, 1, 2, 3, 4, 5. On the 5 position I will have the ester group attached. And that'll be carbon 6 right there. So numbering these chains can be a useful way to make sure we get the product we want. Then the negative comes down, kicks out the OME. So it's pretty much the same mechanism as we've been seeing. And now the OME minus will come in and take off the hydrogen that lies in between the two C double bond O groups, just as it did before. The reason being that this hydrogen is fairly acidic because the anion is stabilized by both of these carbonyl groups. And then we add the H plus in the second step, and we get our product. Okay, let me make a couple of comments here. The first one is about ring size. The most favorable ring sizes are 5, 6, and 7. And we noticed this when we talked about lactone formation as well. So if you want more information about the relationship between ring size and what's most likely, please go back to the lactone formation mini lecture back in test 3. Alright, so we know that 5, 6, and 7 membered rings are going to be the most probable here. And one other thing you'll notice is that we always get a ring size that is 1 less than the length of the chain. So if we've got a 6 carbon chain here initially, we're going to end up with a 5-membered ring. If we had a 7 carbon chain, we'd end up with a 6-membered ring. And that's always because the negatively charged carbon is always the alpha carbon, and it goes around and hits the other C double bond O. One other point I want to make is that some people will ask me, well, why does this negative not come in and attack another equivalent of this? Why does it attack the C double bond O in the same molecule? Well, the reason for that is that this would be done under very dilute conditions. So it would be very unlikely that a negative charge would meet another molecule of the same thing because it's diluted. So it's more likely to come around and hit the C double bond O on the same molecule rather than on another molecule. We call this an intramolecular reaction. A reaction between this and another molecule would be called an intermolecular reaction, and that will not be favored under dilute conditions.